Okay, so let's start. Okay, so this is Deng from University of Southern California, and today I'm going to talk about the Strichartz estimates on generic irrational tori. Okay, so this work is joined, so it have this work contains a few results, and these are joined with Pierre Germain, Larry Guth, and Simon Myerson. Okay, so we start by, of course, by describing the general Strichartz estimates, and we'll talk about then we'll move on to focus on the case of a specifically the case of irrational torus. So that U will be the solution to the linear Schrodinger equation. On here, let's say we have some manifold. Okay, and with initial data f, and then we write u equals e to it delta of f. And we're interested in the so-called Strichartz estimates, where we estimate the LP norm of this linear evolution in space-time, well, for some finite or infinite time interval. I want to know that how can we control this particular quantity by the L2 norm of f. Well, we assume here that this projection Pn, we assume that f has essentially frequency less than or equal to n. So it's kind of a frequency like a localized function in L2. I want to estimate the LP norm of the Schrodinger linear Schrodinger evolution. Okay, so of course you can expect that this is it should have wide application in PDEs, that in especially nonlinear Schrodinger equations, this will be basically some of the basic estimates are relying on these Strichartz estimate. And for example, the so-called XSB theory is also has a close connection with the Strichartz estimates. And as you'll see later, that in the case where M is a compact manifold, if M is compact manifold, then such Strichartz estimates, Strichartz inequalities, they are actually also closely linked to the important problems in number theory. Okay. So we start with a simple case, which is a Euclidean case. So suppose M is RD, then we have this Strichartz, classical Strichartz estimates, where here we can prove the LPLQ estimate, where you have this LPLQ estimate of the linear evolution is bounded by the L2 norm of f, provided that that is PQ satisfies this particular scaling condition. Okay, so in particular, if you apply, for example, if you apply this Pn, this little with Petty projection, and you apply the Sobolev or like Bernstein inequality, you get something like this. So if you look at the frequency n component of f, then the LP norm for R for all time, or especially like 0t, for 0t bound, you get uniform bound in T. For all R, you can bound it by n to this particular power times L2 norm of f. Okay, as long as P is bigger than this 2d plus 4 over d value. Okay, so this is classical, and so this is classical, but for later purposes, let us actually briefly explain the heuristics behind like why we would have such an estimate, why we can control the global space-time LP norm of this linear evolution. Okay, so basic heuristic here is the so-called wave packet decomposition. So in particular, this Strichartz estimate relies on the decay estimate or the dispersion decay estimates, and the idea is that if you imagine f is a so-called wave packet, which essentially you can think f is a wave packet, has frequency c, where times v of x, or v of x is a kind of a nice Schwartz function in x. Then what happens is that if you evolve this particular wave packet, then if you evolve this particular wave packet by the linear Schrodinger equation, then this is basically gets translated at the so-called the group velocity, which is which is the gradient of the dispersion relation, which is 2xc. So dispersion relation, let's say m of xc equals xc square, and then the grad mxc equals 2xc. Okay, so then basically this f, apart from these phase factors, gets translated by this particular group velocity. Okay, what does this mean? What it means is that if initially initially the data f is consists of wave packets at different frequencies, then of course this wave packet will travel at different speeds or different velocity, because if you have because if the wave packet has frequency c, then the group velocity is like twice x. Okay, so in particular, if you start with initial data being a bunch of wave packets at different frequencies, then initially they are like concentrated together concentrated near some specific point in the space, then at later time they will get separated, and they get separated means that essentially the LP norm for p bigger than 2 gets smaller. Okay, so in particular, if you think of it, if you have your initial data have frequency n, then if you choose the time t such that this group velocity times times is of size like 1 over n, what happens in here is that you have initially like t equals 0, you have a bunch of velocities concentrated together, and now at time t they're going to be traveling, like something here, going to travel here, we're going to travel here, travel here. They're going to be separated, and separate means they'll have a much smaller like LP norm. And the time when they start to separate, okay, if you think of it, this 2tc equals n to minus 1, because if you have a frequency, if you have a wave packet of frequency n, then the characteristic scale of this wave packet is like 1 over n by the uncertainty principle. Then if t is less than n to minus 2, then the distance where this wave packet has traveled is less than 1 over n, which is less than the characteristic scale of these wave packets. And then we can think in a way that at exactly time t equals n to minus 2 do these wave packets start to separate. Okay, in particular, if you look at this LP norm, if you think L2 norm is constant, then the LP norm gets smaller if the different pieces with different wave packet pieces begin to separate, and it's big if the wave packets are close to each other. So in particular, in this case, this LP norm will be at the peak for t less than n to minus 2, and then will start to decay, and it actually for L2 function as f, it will for suitably nice function f, it will decay to 0 at t equals infinity. Okay, and of course, if you calculate the LP norm like in space and time for t less than n minus 2, then by simple scaling argument, you get exactly this power you expect for the Strichartz estimate. Okay, so this is the kind of a very simple heuristic behind the Strichartz estimates on Rn, because due to dispersion, this LP norm will only have one peak at time equals 0, or time almost up to time n to minus 2, if your data have frequency n. Okay, so now we turn to the case where you have this M is a compact manifold. If M is a compact manifold, then actually as you see this wave packet will travel, like in the case of Rn, travel in straight lines. In the case of compact manifolds, you will travel by geodesics. And since you have compact manifold, these geodesics will come back, and this will create like concentrations, again, like reconcentrations at later times, which makes this particular LP norm gets big at some later time. Okay, so exactly when this happens, how this happens actually depends on the geometry of M. So consider two cases. So one case is a standard square torus. Then again, we have this wave packet, except that this X is considered like the mod 1. So in particular, if you think C is a frequency, C is a integer value of frequency, then if t equals 0 and or t equals 1, this x plus 2tc, they correspond to the same point. So if you have wave packets, like in the Rn case, it just goes to all the way to infinity. But in the case of a torus, of course, it goes here and then it will come back here. Okay. So in particular, in the case of a standard torus, we have this reconcentration or sort of refocusing at this time t equals 1. So at unit time, because all your frequencies are integer vectors, and so the group velocities are integer vectors. Okay, so what this corresponds to is the fact that we have the same Strichartz estimates on the irrational torus, sorry, on the square torus as it is on the Rn, but not for all time like t0 infinity, but only for time t from 0 to 1. Because at time 1, these wave packets, they get concentrated again, and then you have a second peak of the LP. Okay, of course, this is easier stated than proof, and the proof here is actually a very nice recent work of Bourgain-Demeter, which applied the theory of decoupling, and actually later Killing-Vincent actually proved a sharp version without the derivative loss. In the case p is bigger than 2d plus 4/d. Okay, so this is the now classical result of a Strichartz estimate on the square torus. In particular, if you consider the Strichartz estimate for time 0 to t, then you get this factor 1 plus t to 1 over p, which is certainly sharp because you have this Schrodinger evolution is periodic in time. Okay. So now you have seen two cases: the case of Rn and the case of torus. You see, we get this optimal in the Rn case. We just have one. We just have one. Okay, in the torus case, we have this particular value which corresponds to the second peak time at t equals 1. Okay, so this is a case of Strichartz estimate on torus. So we briefly mentioned the case on the sphere. In the sphere, actually, it's well known that the Strichartz estimate will only hold for time 1, and moreover, it will hold with some derivative loss. Heuristically, this is because that in the case of sphere, all the geodesics have the same lengths, actually have the same periods, and so if you have like any starting point, you go through like different geodesics, then all these like wave packet that goes through all these different geodesics, they will come back at the same time, which is actually much less than 1 if you think the frequency or the group velocity is very much bigger than 1. Okay, this means that this so-called second peak, or the reconcentration, actually happens very quickly, like if you have high frequency inputs, and then this means that you are expecting to have a very big value of this LP norm pretty soon, and you will expect some loss in the Strichartz estimate if you think of time 1 Strichartz estimates. Okay, so the second peak comes in a very short time for high frequencies, which lead to derivative loss. To see these cases, like the case of torus versus the case of sphere, actually demonstrates that there is a role of geometry that is played in this Strichartz estimate, especially in these unit time Strichartz estimates. Of course, this is still not very well known. In particular, it is not known what is the optimal Strichartz estimate for the negatively curved space. But in any case, it's not the topic that we want to study today. So what we want to talk is that even in the case where we have the same geometry, let's say we just think of tori, we always have the the standard standard tori will always have the flat geometry. Then do we still have something different, like something that we can explore, like that makes a difference in terms of Strichartz estimates? Okay, so in the case of particle effect geometry, there is still something interesting going on, which is the subject that we'll be looking at. Okay, so now we consider general rectangular torus. So if you think of it like the square torus is you will have like a square like with equal side lengths. And now if you think of a general rectangular torus, it's like a box of size like lambda 1, lambda 2. So you have lambda 1, lambda 2, lambda d. And you make this box into a torus, where lambda i's are like a generic, like general positive numbers. Then again, of course, you get this. We denote this by t lambda d, and we think this is always a flat torus having flat geometry. Okay, so when lambda equals 1, we get a standard square torus. If you think lambda j, these ratios between some lambda j square and lambda k square is irrational, we get the so-called irrational torus. Okay, so it is, if you consider the case of irrational torus versus the square torus, then if you consider Strichartz estimates, then it can be shown that if you consider time 1 Strichartz estimates, they are the same. For example, it's also follows from decoupling proof of Bourgain-Demeter. But what's different is that if you have so-called generic irrational torus that we shall define below, then the same Strichartz estimate actually holds for time intervals which is much longer than 1. Okay, so we'll show this below, but first, if you apply the heuristic argument, you'll see like why this will be true. Okay, so now the geodesics. Okay, so we have a general like irrational torus, then the geodesics will almost periodic instead of periodic. And then if you think of it like in the case of a square torus, like all the geodesics, they reconcentrate at time 1. But if you have this almost periodic geodesic, they will reconcentrate it usually as at like a much later time. Okay, again we look at the corresponding like again we look at the specific wave packets at frequency c, and then you have this it travels at the group velocity 2 xi, where xi is has a frequency of size n. Now in the irrational case, xi equals lambda 1 k1 lambda d kd, where k1 kd is like an integer vector, and lambda 1 and lambda d are like the parameters the parameters of the torus. So lambda j plus. Okay, so what happens with this? Like, when does these geodesic like go back to the original place? Okay, suppose this v is a wave packet of frequency, and then again its space characteristic scale is 1 n to the minus 1. Okay, so then what happens? Like, at what time do you have the second peak? What time do you have second peak? Means that if you have any like integer vectors, any frequencies like kj, if you have any frequencies kj, then the time. Okay, so this is the distance traveled. You know, the displacement. Okay, and this is this displacement. I mean displacement in the jth coordinate, and this is a period, spatial period. Okay, so displacement divided by spatial period should be like really close to an integer, because you want because the torus is periodic, and you want the wave packet to come back to the original position to have this reconcentration. So this displacement divided by the period has to be close to an integer up to a distance which is n minus 1, which corresponds to the characteristic scale of this wave packet. Okay, so in particular, in order for all the wave packets starting from 1 point, all the different wave packets starting from 1 point to go back to exactly the same point, at time t, we must have this inequality being true, that the fraction part of this quantity 2 lambda j kjt divided by 2 pi divided by lambda j must be close to an integer up to an error of 1 over n. Okay, and this has to be true for all the possible integer frequencies. So for all the possible frequencies kj, because if you want all the different wave packet starting from this point to come back to reconcentrate at this particular at this point itself. And of course, this is essentially equivalent to saying that if kj is like n, then like this essentially like a lambda j square, t lambda j square of divided pi, forget about pi, then you have like t lambda j square times kj has fraction part less than 1 over n, and it's true for any kj up to n, which means that this lambda j square t, the fractional part of this lambda j square t has to be less than n minus 2. So let me remark that the fractional part is the minimum x minus n or n in z. Okay, so just essentially the distance to nearest integer. Okay, so now you see that suppose we have irrational torus. Here it doesn't have to be irrational. Here for any torus like lambda j, like in order for the reconcentration to happen, for the second peak to come, we must have this like inequality that holds for j from 1 to d. In particular, it means that this lambda j squared t over pi has to be really close to an integer in order for this to happen. Okay, so the point here is that suppose we have a lambda j square being irrational and being like a generic, or just it doesn't have to be generic, just have to not very, very special. Like then the fact that this lambda j, each lambda j square t over pi being close to an integer, it puts some non-trivial restriction, particularly puts some non-trivial lower bounds on this time t, and which is what we want, because if we know that reconcentration time has a lower bound, then we can expect the same Strichartz estimate to happen on a longer time interval. Okay, so let's say in the simple case d equals 2, let's say lambda 1 equals 1 and lambda 2 equals lambda 2 square equals beta, where beta is a real number. Okay, then we need to find the t such that, let's say t over pi, let's just say t is close to an integer, and moreover beta t, so lambda 1 square t and lambda 2 square t, they both have to be close to integer. Let's say t is close to integer m and beta t is close to integer, that means beta m is close to integer. The point here is that it is known in Deng approximation that if you have some beta, unless this beta is very, very well approximated by rationals, otherwise, if you think m is an integer and beta m is close to an integer, then m must have a lower bound. M cannot be too small, and it must have lower bound. With lower bound depends on the distance of beta m to the nearest integer. Okay, and this actually turns out to be dependent on the Deng property of beta. And of course, there's a lot we can say about Deng properties. But here we'll just focus on the simplest case where we have a generic beta. A generic beta means that we're considering all the beta except all the beta like in R plus except for like a set of a measure 0. Okay, so let's say so in general, like for general beta, this is a question like how to bound this nearest this distance of beta m to the nearest integer, how to bound it below by negative power of m. This is linked to the Deng property of beta. And for generic beta, we can choose this power like minus kappa to be minus 1. Okay, so for generic. Okay, so for we have beta m bigger than m to the minus 1, actually log m to the minus 1, minus 2, let's say. Okay, so this is a standard theorem in divergent approximation, and is proved easily by a probabilistic argument. That's we'll omit the proof. So this is the theorem of Kinching. Okay, so now what does this imply for our Strichartz assay problem? In general, if you have d dimensions, you have a similar result. That if you think lambda j squared t is close to an integer, for each j, then basically you see this maximum of this shortest nearest distance to integers is bigger than, again, a negative power of this capital T. And in the case of generic parameters lambda 1 and lambda d, we can actually show that this value kappa is minus is 1 over d minus 1. That's to say this maximum is bigger than this particular power of t. Again, this is proved by a probabilistic argument. Okay, so now you have a lower bound of these shortest distances. On the other hand, if you want to have reconcentration, you must have an upper bound of these shortest distances. Then if you match these two bounds, you think n to the minus 2 equals t to the minus 1 over d minus 1, you get this expected time, which is t equals n to 2d minus 2. Okay, so this is what happens for generic, at least a generic irrational torus. You get this due to divergent approximation, due to divergent conditions. You can actually get this reconcentration phenomenon happens at a much later time than in the case of a rational or a square torus. Okay, so now this is kind of the thing that we would guess, that suppose we have wave packet of frequency n and we have a physical scale like 1 over n, then the same Strichartz element we would expect it to hold up to time t equals n to the 2d minus 2. Okay, so turns out to be another a scenario that we also need to consider, which plays a role. So this value, this n to 2d minus 2 value, plays a role for large t, and this second scenario plays a role for smaller t. That is, if you think f has frequency n and frequency frequency n, but it doesn't have physical scale 1, have physical scale like 1 over n, then what happens is that this LP norm will not have a peak, but it will have it will remain constant for a pretty long time. That's for time t. And if you do the calculation, then they will suggest that you have the same Strichartz estimates up to this particular time. It's t to the n, t equals n to the pd over 2 minus d minus 2, if this f has frequency n. So this if okay. And because of these two considerations, we were led to the following conjecture about this this long time Strichartz estimates on generic torus, which is his conjecture we did with Pierre Germain and Larry Guth. That is, for generic choices of parameters lambda, we have the Strichartz estimates. If f has frequency n, then Strichartz estimates holds. The same Strichartz estimate with the same power, holds up to this value n to the gamma, and where p is bigger than this critical value 2d plus 4 over d, and gamma is something up to some positive thing up to this value gamma of p, where gamma of p is the minimum of 2d minus 2 and the pd over 2 minus d minus 2. Okay, so this is a conjecture about this long time estimate. Instead of time 1, now the same Strichartz estimate with the same right hand side now holds for time up to n to the gamma, where n is the frequency of the function. Okay, as a corollary, you can see that we have this LP norm up to time t is bounded by 1 plus n to the minus gamma over p times T1 over P times the same thing as you see in the case of a rational torus. So you have this extra factor, which is the improvement we get from irrationality. Okay, so now what we are able to prove in the work with Germain and Guth is a part of this conjecture. We have proved this conjecture, this full conjecture in the case where P is bigger than or equal to 6. In any case, we get exactly this value, and when P less than 6, we get something got some positive value of gamma that but doesn't really reach this conjectured value. So that's what we prove. So generic lambda, this Strichartz estimate is true provided gamma is up to this gamma 0p, or gamma 0p is 2d minus 2 is a sharp exponent for P bigger than or equal to 6, and is some value which doesn't reach the conjectured exponent when P is less than 6. But the point here is that like although we don't for gamma for P less than or equal to 6, we don't get a full range, but still we get that the Strichartz estimate holds for some for up to time n to gamma for some positive gamma. So this is a long time Strichartz estimate, especially when n goes to infinity. It's a long time Strichartz estimate. Okay, so this is our first theorem. And so let us discuss also a case when we have like a more general, like a non-rectangular so-called tilde torus. So in the previous case, we're considering the torus being the product of one-dimensional torus like this, which means you're doing like a rectangular box as a fundamental domain of torus, and then it's a rectangular one. And now, of course, in general, you can also consider the case of a non-rectangular one. We have a general like a parallelogram of okay, let me draw it here. I have a general parallelogram of this form, and again, you can make it you can turn it. You can turn it into a torus, and then that has a flat geometry. Then what would happen if you try to consider Strichartz estimates on this tilde torus or non-rectangular torus? Okay, and as you would expect, if you think that the improved long-time Strichartz estimate for the irrational torus come from the genericity of all these, coming from all these choice of parameters, then if you have an irrational torus, you will have more parameters and you have more genericity. So you should be expecting a better, like a strictly better result than what we get for the rectangle. Okay, so here's what we get. So imagine you think this non-rectangular torus is given by this particular basis of the vectors, and we have this like general like generic like symmetric matrix on RD. Then this result we proved with Germain and Larry Guth and Simon Myerson, which is slightly later than the previous one, is that that's in the case of 2 dimensions, like if P is bigger than or equal to 10, then we have this okay, so this exponent is exactly the same exponent as you see in the case of standard Strichartz estimates. Then the same Strichartz estimate as you have for the rational torus now not only holds for time 1, but for time n to the 4, where n is a frequency. Remember that if you have the the square, so the rectangular torus, then this power would be like when d equals to this power with 2d minus 2, which is 2, and this result shows that in the case of a generic like non-rectangular torus, you're having an improved result where you have this n to the 4 instead of n to 2, and consequently you have this bound on T with this factor. And for P less than 10, we have some non-sharp results that we're not going to show here, but again, these are improvements of corresponding results in the for the rectangular torus. Okay, So these two results are the results about this long time linear Strichartz estimates. And now let us okay, so for the second part of the talk, let me discuss a little bit about the possible applications of these results. We have found some applications, and the thing we'll be talking about is application to the question of growth of Sobolev norms. Okay, so this is something that has been studied, since like 90s, and since for the last like 20 years. Now consider, a nonlinear like Schrodinger equation. Sorry, I mean a nonlinear Schrodinger equation. We have this IT plus Laplace of U equals this power law of nonlinearity on the torus, and here the torus can be square torus, can be irrational torus. Now it is it's well known that this such nonlinear Schrodinger equation in the defocusing cases have a positive like conserved energy. That is, you see that is essentially at the level of H1. Okay, and we have this threshold like which is with this threshold P, which is like this particular value which determines whether the function is critical or subcritical or supercritical in H1. Essentially, if P is bigger than this value, this PC, then this equation is supercritical. If P is less than PC, this equation is subcritical, and if P equals PC, then this equation is critical on the H1 level, on the energy level. Okay, so we talk a little bit about the Goal-Poisson results. Like the Goal-Poisson result, we have Goal-Poisson in H1 in the energy subcritical case, and in the energy critical case, there has been some it is quite tricky, and was proved recently by the work of Svekov, Ionescu, Prosser, and Strunk. Okay, so essentially the idea is that if P is less than this critical value, then you have Goal-Poisson in H1. If P is equal to this critical value, you also have Goal-Poisson in H1, but it's much more difficult. Okay, so the question of growth of higher Sobolev norms concerns suppose P is less than or equal to this critical value, then your solution is like exists globally and is bounded, because of the energy. This solution is bounded in H1, and the question is, how does the HS normal solution behave when S is bigger than 1? So physically, it essentially means that if you have a solution like on a torus, then the solution will be supported in some particular frequencies. And then if you think the H1 norm is constant, H1 norm equals constant. If you think of HS norm, if it goes to infinity, then it will be suggesting that these solutions are kind of shifting to higher and higher frequencies at time infinity. So this means we have high frequency. Okay, and this is in physics. This is roughly described by the term of wave turbulence. This is a very vague word, but in some settings, it's described very weakly as this growth of Sobolev norms. Okay, so this is a question. So suppose we have a solution that is in H1. What can we say about the HS normal solution for S bigger than 1? Okay, so there are some results. Like up to now, there are some known results about the behavior of HS solution, although still not very much. So this work of Coriander, Q, Stephanie, Takoka, and Tao is the work around like 2005, where they proved that this HS norm can be arbitrarily large, but they don't know whether it actually grows to infinity or not. Okay, and the subsequent works of different people will not mention all of them. It's obtains growth, for different cases, different settings, different models. Okay, so by the way, this general term weak turbulence or wave turbulence, it describes a lot of, it can be used to describe a lot of things, and there has been especially in recent years, there has been many different studies like of this topic, like from different aspects, from the work of Frau Germain and the Buckmaster Germain Shata, which has to do with the normal form approach, and the more recent work of Claude Germain and the work of Hani with myself. We did the case of the wave turbulence problem with which is associated with this random data setting, which is kind of more physical setting, but of course we're not talking about it. But it's just that this is a general like thing, and the growth of Sobolev norm is just one small piece of this big picture. Okay, so on the other hand, one may also ask like what can we have for the upper bound of this growth of HS norm, and it's believed that of course, this is a big conjecture, I think attributed to Bourgain, that for generic solutions, you may have growth of this HS Sobolev norm, but this growth will not be too high. Essentially, will be kind of logarithmic and normal. Of course, currently no one is any place near the proof of this conjecture, but we still have some like non-trivial partial results. This okay, so it has improved in some setting for the linear Schrodinger equation, but never for the nonlinear Schrodinger equation. Okay, and what we know is that we have some not logarithmic growth, but some polynomial growth upper bounds for the growth of HS norm. Again, this is due to a bunch of people, Bourgain himself and Stefanini, Schrodinger, and Collier, Kwon, and O, and the Planchon, Svekov-Visiglia, and I think there are more recent work that didn't put it in, but these are some results. Essentially, the form here are like like U to the HS less than T to the like C times S minus 1. For an S bigger than 1, we'll assume subcritical P less than PC. And all these results are in the energy subcritical case, as we explain below why we must have subcritical. Okay, so of course the natural question is like what would happen? What can you say about this growth of Sobolev norms in the energy critical case? Okay, so technically this is because that's the kind of thing, the main techniques that they use to prove this this polynomial upper bound, which is so-called the high-low method of Bourgain, or the I method of the CKSTT group. So this method requires that you have some room, like in the estimate of the energies, or in the local hypothesis proof, and this some room precisely corresponds to the fact that you must have a subcritical nonlinearity. That this subcritical means that this P is strictly less than this PC. Okay, so if you remember that when P is less than PC, this is easy to prove, to have like hypothesis in H1. If P is equal to PC, you still have hypothesis in H1, but it's a much weaker form of hypothesis, and it's much trickier to prove. And that is precisely because you don't have this enough room for the in the proof of hypothesis. And again, the same comment applies here, that if you have an energy critical case, then you won't have any room in the Bourgain's high-low argument, and then you won't be able to get this polynomial growth result. Okay, so that is where this irrationality result comes in. So for generic irrational torus, we have this long-time Strichartz estimate. If you think of it, like the standard Strichartz estimate is saying that your solution. Okay, so let me say standard Strichartz estimate is like a U to the LP of 0, 1. Okay, so less than n to the I think half d minus p d plus 2 f to the L2. So this is standard estimate. Now, if you want to kind of break the scaling, you want to improve this to to have a better scaling. You want to decrease the power on right hand side, but unfortunately that is impossible because that's why you have this scaling. This is impossible to improve the right hand side. But this long-time Strichartz estimate precisely allows us to improve the left-hand side, namely that if you have this becomes then improving the left-hand side, and this is exactly what allows us to break the scaling barrier that you are having this that because you're having this particular improvement here. You can compare this with the case of RD case. In the RD case, it's well known that you have bounds. Suppose in fact you have scattering, so your solution is approaching a linear solution. And that is, in some sense, this can be attributed to the fact that you have Strichartz estimate not only for time 0, 1, but for all time like all time up to infinity. And now instead of time infinity, you have this time n to gamma, but it's still a long time. It still allows you to break the scaling barrier, and allows you to get the same results in the critical case as one would get in the subcritical case. Okay. So this is the result we have for the energy critical Schrodinger. So we're considering this for the 3D like p equals 5, the quintic Schrodinger, which is energy critical, which is energy or H1 critical. And then suppose your initial data in HS, and if we assume that this parameter lambda is generic, and assume that that the energy is sufficiently small, then you have this polynomial upper bound on the growth of these high Sobolev norms, and which is HS norm being less than the constant polynomial power of T. Okay, so this is the third, one of the main applications of these results, which has to do with this upper bound on growth of Sobolev norms for energy critical nonlinear Schrodinger equations. We also have like a result for subcritical case that we get some improvement of this generic torus compared to the rational torus that we're not going to describe here. This is drawing work with Pierre Germain. Okay, so this is essentially the results. We started with this long time this long-time Strichartz estimate. We're applying it to prove these results for the nonlinear Schrodinger equation. Okay, so finally, let me spend like 5 minutes briefly going over the proof. So the case of in order to prove the results, let's say we look at the case of the long-time Strichartz estimate for in 2 dimension, and let's say for p equals 6, L6 Strichartz estimates. The idea is that okay, so again you set this parameters lambda1 equals 1, lambda2 square equals beta. Again, initial data being this given by this Fourier series with L2 norm being 1. Then we can just as we're familiar with, this is the linear Schrodinger evolution is given by this particular Fourier series where this QK is a quadratic form which is associated with this irrational torus. Okay, so now we measure the L6 norm, which you can write in an algebraic form, which essentially the L6 norm is basically like a T times this kind of thing, and if you apply the Cauchy-Schwarz, this can be controlled by the upper bound of this counting problem. So this counting problem here, you're counting the number of vectors K2, K4, K6, such that this quantity, this sum of these quadratic forms QK2 plus QK4 plus QK6 equals this like O of T to the minus 1. Okay, so here again, V is a V is a constant vector and B is a constant number. So this is kind of standard when improving the Strichartz estimates for the even like integer powers. Okay, and so then you see that since we are reduced to this counting problem, and the key point of whether this Strichartz estimate holds true or not is to ask whether this particular quantity the sum of these quadratic forms. If you consider these vectors k2, k4, k6 like ranges over a particular like plane where k2 plus k6 plus k2 plus k4 plus k6 equals constant, you want to know whether how this quantity is distributed, whether this quantity is kind of uniform, like uniformly distributed when k2, when these vectors ranges over this linear manifold. Okay, so for square torus, it can be shown that using the classical number theory, it can be shown that this quantity, if Q is a square torus and Q is is just x squared plus y squared, then of course Q is an integer. So these quantity always take the integer values. So the only thing you can say is that this quantity is uniformly distributed at scale 1, like at scale 1, which means that the probability that that this quantity belongs to any interval of length 1 are roughly equal. Okay, so this is kind of a standard square torus, and you can say nothing more about that. And it turns out that this exactly corresponds to t equals 1 corresponds to the fact that you're having this this Strichartz estimate for this time interval 0, 1 unit time. Okay, so now the point is that if you have generic beta, then this quantity turns out to be almost uniformly distributed, not just for time, just for scale 1, but it actually holds for a finer scale, which is 1 over t, where t is about n squared in the 2-dimensional case. And this follows from this uniform distribution of the quantity where you have m1, m2 random integers, and beta is a generic irrational number. Then for some particular range of m1, m2, then this quantity will be uniformly distributed. If you think of a beta is an irrational number, then the range of this, the distribution of this quantity will be kind of much more uniform than if this quantity only takes integer values. Okay, so this is one of the reasons why we would have this improved Strichartz estimate, which essentially here boils down to the equidistribution properties of these irrational quadratic forms. Okay, so I guess we have like we have 15 minutes, so I think we'll try to stop, but we'll skip this part. And okay, so we discussed a little bit of the proof of the gross or Sobolev norms. We spent just 3 more minutes on this proof of the gross or Sobolev norms. So now we consider the nonlinear Schrodinger equation. So if you want to bound the gross of the HS norm, so the standard method is by the Bourgain's high-low method, or later on the CKSTT group that developed the method called upside down I method. So the idea is that H1 norm is linked to the conserved energy. Now HS norm, if S is bigger than 1, it isn't linked to any particular conserved energy. However, you can try to construct a modified energy that is at the level of HS norm. That is not really conserved, but it's almost conserved in the sense that its time increment. It has a very nice control. Has a very nice control. Okay, so here we choose a frequency n, and we choose a Fourier multiplier dn that is kind of the s minus 1 order derivatives for high frequencies. It's kind of 1 for low frequencies, and then we define this modified energy, which is the E of dn of u. So dn is at level of HS, then this E of the energy of dn of u would be like at the level of ds. So dn is at the level of s minus 1 derivative. So this modified energy will be at the level of HS. Okay, so the idea is that we want to control this value, like the evolution of this quantity, and we want to say that suppose this quantity is less than 1, then the increment of this quantity on time intervals 1 is less than a negative power of m. In that sense, this quantity is almost conserved. Okay, so essentially this is the thing that people can get in the energy subcritical case, namely if you define this energy, try to match the exact conserved energy structure of the equation, then you'll get some cancellation done, and you get a result, namely that if this particular energy is less than 1, then the increment of this energy on intervals length 1 is less than n minus gamma. And then you can iterate, you get that this energy is less than 1 for for some much longer time than 1. And then from this, you could deduce the upper bound, the polynomial upper bound on the growth of Sobolev forms. Okay, so this is the result in the subcritical case, and this n minus gamma is precisely due to the fact that you are subcritical and you are having some room, in the local opposed argument, and then which leads to this case. Now, in the critical case, if in the critical case you won't have any room here, and you won't have this n minus gamma, this negative power on the right hand side, and all you can have is that this is less than 1, and this is, unfortunately, this is sharp. You cannot hope to improve it, just that you cannot hope to improve the unit time Strichartz estimates on the right hand side. And if you have this, of course, potentially this E and this modified energy would grow, multiplied by a constant factor if you go for time 1, and if you go for time t, it could grow to exponential in t, which is not the polynomial upper bound we would expect. Okay, so now here's the thing: like why does the long time Strichartz estimate help? Is exactly because if you have long time Strichartz estimate, then essentially this unit time bound is proved by the unit time Strichartz estimate. Now, if you have long time Strichartz estimate up to length n to the gamma, then you can actually have, this bound, again, right hand side is 1, but the left hand side here is not 1, but it's like, is n to the gamma. But that is essentially the same thing that you want to have, because even if you have the previous this subcritical result, you're going to iterate it to get this unit increment for this very long time up to time n to gamma. But now you already have this bound unit increment up to time n to gamma. And here it is using the long time Strichartz estimate, where you have this, let's say this Strichartz norm up to time n to gamma is less. Okay, so this is a key thing, that why these long time Strichartz estimates can be used to prove the bounded growth of Sobolev norms. And there are some technical things about how to prove these estimate for nonlinear equations. We will skip that. And of course, there are few other questions. So how do we improve that? Of course, we still don't get, in either case, we are not fully getting a conjecture, especially for small values of p, where we don't have this counting estimate available. And how do we do that? That will be one of the interesting questions. And again, like the other question, how to generate other geometries, the other equations, other settings, and whether or not you have large data problems. So any case, so you can, there are interesting questions related to this conjecture itself, and interesting questions related to partial nonlinear applications. So especially if you have any relation with random data theory, in the case of irrational tori, there's some now we have some results that demonstrates the irrationality, the use of irrationality also in the random data setting. But in any case, so we'll stop here. So okay, so we'll stop here. Okay.